If you recall, the last time we spoke, we were talking about that relationship, that it was that question I asked you about whether or not the strength of the intermolecular force is more about the size differential between the two, or if it's the same. So this is just a summary slide of that question from Monday, right? When two molecules have comparable molar masses and shapes, dispersion forces are roughly equal. But then when two molecules have different molar mass and there is no hydrogen bonding, dispersion force determines the dispersion. Dispersion forces determines the substance with stronger interactions. So basically, it was just a summary slide from the question I gave you last week, and we didn't because I think the last thing we did was answer that question and then we left, right? Okay, so um, this week we'll be talking about mostly. I'm not this week, sorry, today. We'll be talking about mostly phase changes and interactions with water, with other molecules and stuff like that, and water's properties and stuff. Turns out that water is a very special molecule. I think I told you that before too, because we saw that water was like the only one that had hydrogen bonding to itself with oxygen, right? And it was like a really high boiling point, and then on that chart, but everything else was like really low boiling point, so it's really special. So one of the reasons why is because, like I was saying before, hydrogen bonds on water, they bond to each other, and that gives them a lot of strength, and so it takes a lot of energy to break them apart. So over here we have hydrogen bonding in ethanol, right? And if you didn't know this, water and ethanol are actually miscible, which means that they can dissolve within each other, right? I mean, you probably do know this because most beer is 7% alcohol, right? And Everclear is 90% alcohol. I think so, right? 190 proof, 95% alcohol. My favorite Captain Morgan is 22%, I believe. So when you hear these things about liquor and drinking and beer and all that, you can't really tell that there's a mixture of alcohol and water. You know it is because you're drinking it, right? But when you look at like a bottle of vodka, it just looks like one clear liquid, right? It looks like one clear liquid. And so that's, by definition, miscibility between ethanol and water. And the reason why that happens is because ethanol has this shape right here. And generally, this shape over here, this part over here where the hydrogens and the carbons are, it's super nonpolar, right? And when it's super nonpolar, generally those kinds of things don't like to be miscible in water. And a good example of that is when you have oil in water. Oil is mostly CHs, right? Carbons and hydrogens. And when you put oil in water, it definitely doesn't mix, right? It definitely doesn't mix. In fact, we had a question. Was it this class? I don't remember, but one of the clicker questions was like, "Is water more dense than oil?" or something like that. Was that you guys? Oh, good. Anyway, water is not more dense than oil. Oil is sorry, water is more dense than oil. Oil is less dense than water because when you put oil and water together, the oil rises to the top, right? You see that when you're washing your dishes and all that, the grease goes up to the top. So when you have oil, it can't do any hydrogen bonding because it's mostly made of hydrocarbons or carbons and hydrogens, right? But when you look at ethanol, which is this, its thing is what is this formula again? Where's my Apple Pencil in my pocket? I always lose my stuff. The pen. There we go. So ethanol's structure is CH3, CH2, OH. And so you can see here that you have a hydrogen right there, right? And that hydrogen is bonded to an oxygen that has what on it? Two lone pairs, right? Which by definition means that hydrogen bonding can occur with ethanol. And since hydrogen bonding can occur with ethanol, right, water can surround that hydrogen bond. Water can solvate ethanol by surrounding the hydrogen bond, right? But much in the similar way as it does with salt and sodium and chloride, right? And that's why ethanol is miscible in water. And you can see in this little electrostatic thing here that it's got a hydrogen bond going on right there, right? It can do it to itself, and it can do it to water. So that's why ethanol is miscible. So the reason why we're talking about that is that attractive forces and solubility follow this one rule. It's changed over time, right? And so it used to be like likes like, right? Now it's like dissolves like on this slide, right? But a friend of mine is like an expert on solvation, and he's got a PhD in literally just dissolving things because apparently it's a big business these days to clean things, with the pandemic and all that stuff. And so his literally his entire career in PhD in chemistry is about dissolving things, and he says that it's no longer this anymore, even though that's what the textbook says. Now it's like seeks like. And what that means is that when you have a molecule that's not the same molecule as another molecule, but similar in shape and similar in and intermolecular forces and similar in polarity and similar in all those kinds of ways, but not the exact same molecule, right? They seek each other, right? And they dissolve each other, right? They like to be together. So this is when we get dirty again in chemistry, right? Part of the periodic table we learned already last week where opposites attract, right? Positive and negative attract each other, right? On the periodic table. But then you also learn too that the diatomics like each other, right? They like to be with each other, right? And so, it's no surprise that the periodic table, a lot of people call these groups, the numbers at the top, right? Group one, group two, but they used to be called families, right? Family one, family two, family three, right? And so when I say things like, in this family, chlorine and chlorine get together, right? It's quite literally two chlorines in the same family, right? Like so, like two brothers or something getting together, right? And then you can say cousins because they're families. They're like, so this is the immediate family. Let's say the halogens are, right? They're like the immediate family, but then like there's like your uncles and aunts over here. So when they like to deal with each other, that's like a cousin with another cousin or something like that, right? So maybe the reason why they changed it to groups is because it's so like it's so incestuous sounding when they talk about it. Um, but the point is though, the other than the brother on brother stuff and the cousin stuff, they usually like to be opposites attract on the periodic table, right? They usually like to be opposites attract. So when you look at solutions though, or sorry, not solutions, but when you look at liquids though, it's actually a completely different thing. In liquids, it's not opposites attract, it's things that are alike attract each other, right? So have you ever tried to clean something with water and it just would not pick it up? Right? So for example, if you're like frying a steak on your frying pan and all this butter just spattered all over the counter, right? And you just got a thing of water and you try to wipe it down, does it clean up the butter? No, it just smears the butter all over the place. And the reason why is because water and oil or butter, they don't mix. They're not like each other, and so they won't dissolve each other, right? So what do? You get Dawn dish soap, right? Dawn dish soap is actually the best thing to use to clean up grease. It gets super soapy, and you have to clean up the soap afterwards, but it sure does cut through the grease. And the reason why is because of chemistry. Dawn dish soap, and I mean, I think it was the best marketing campaign ever when they came up with the duck and cleaning ducks. Because I literally buy Dawn dish soap just because of the duck, right? When we clean the oil off the duck. And the reason why they can do that is because this soap, quite literally, I mean, all soaps really are made of this thing called sodium dodecyl sulfate or sodium lauryl sulfate. I promise you, if you go home right now and you look on the back of your shampoo bottle, you look on the back of your hand soap bottles, everything that has some kind of bubbling effect on it, right? That is like a soap, has sodium lauryl sulfate in it, right? And sodium lauryl sulfate is literally a ionic form of a fat, right? So literally you're using a fat to clean a fat, right? A bunch of hydrocarbons to clean another hydrocarbon. And that's why Dawn dish soap works so well. Or any soap, really. You don't even have to use Dawn. You could use hand soap and it'll clean up the butter, right? So, and the reason why this worked, like I said before, is because like likes like now, or like dissolves like, or like seeks like, right? They like to interact with each other when they're like. I mean, it's not just that too. When molecules are similar, they fit together better. You know, they can like sit end on end and fit together better. Their polarities are similar, so they can fit together easier. So that's why that works. So long story short, which I already told the long story, miscible liquids are they always dissolve each other. Okay, so for polar substances, right, things like hydroxide, aldehydes, carbonyls. This is an acetate right here. This is ammonia, and then chlorine, right? Those hydrophilic groups right there. There are things that like water and they'll dissolve in water, right? So if you like water and you're similar in polarity to water, right? You're called hydrophilic because you like to be with water. So the Greek for liking something is philic, right? Hydro is water. So hydrophilic means you like water. So the opposite of that is for the nonpolar molecules, they only dissolve in nonpolar solvents, right? They only dissolve in nonpolar solvents. And what happens is that those are called hydrophobic groups because phobic means scared of something, right? Hydrophobic means to be scared of something. Um, and so, which is really funny because my girlfriend is like an arachnophobic. She hates spiders. And for Halloween, I'm going to decorate the entire house in like fake spiders. It's going to be great. So it's going to be awesome. So, and she's not even gonna know because the day I do it, she's gonna be at work and she's gonna get home super late. And so she'll come in the house in the dark and she'll turn on the lights and literally the entire house will be covered in little spiders. But they're not real. Oh, that's scary. It's about tarantulas? Well, so the thing is like so one of not only am I me and her like Star Wars fans, we're also Harry Potter fans, of course, and so there's Aragog the spider with his little babies, and so the reason why we're gonna have all those spiders is because I'm gonna have Aragog sitting on her like couch. She comes in, and there'll be like lines of spiders coming out. It's gonna be great. It's gonna be a great time. It's Halloween. It's Halloween. It's totally Halloween time. I, I'll come up with something a little bit less scary next year. That's my idea for this year. I can't change it now. I've gone too far with it. I've already invested in too many spiders. So it's too late to change it. Anyway, so if you're hydrophobic, it means you're scared of water. So you're not going to dissolve in water. And so, like I was saying before, things like soap actually dissolves in water too. But sorry, what is it? Oils. Oils are all made of CHs, right? So they're called hydrocarbons, and they're hydrophobic. They're afraid of water, so they try to stay away from water, and that's why you see them sticking at the top when water is at the bottom. Carbon is also, and it makes sense because carbons are not very polar either, are they? Right? Carbon and carbon are like in the middle of the periodic table right there. Neither super positive or neither super negative, so they're not very polar. So many molecules have both hydrophilic and hydrophobic parts. Solubility in water becomes a competition between the attraction of the polar groups in the water and the attraction of the nonpolar groups for their own kind. So what that means is that if the attraction between the water is stronger than the attraction with something else, then the water will stick together, right? And the hydrophobic stuff will stick together. And so that's this thing called hydrophobic effect, right? That's what that is. Um, and like I said, you see it all the time when you're working with oil and water. So speaking of that, these are called immiscible liquids, the ones that are not, they don't dissolve in water, right? And what I just said what I just literally just said is being said here now, right? Water is a polar molecule. Pentane is a nonpolar molecule. The attractive forces among the water are much stronger than the attractive forces between the pentane molecules. So the result is that the liquids are immiscible, right? So here we have pentane at the top and water at the bottom, right? You can also see that the water molecules are closer to each other, right? So it makes that water more dense, whereas the pentane molecules are less close to each other, so it makes the pentane molecules less dense, and so that's why it has it where the pentane is at the top and the water is at the bottom. Now, if it were reversed, right, and the pentane was more dense with more molecules stuck to each other, right, closer to each other, then what would happen? It would be more dense than water, and then it would be at the bottom, right? So all you really have to do to achieve that is that water is 1 gram per mil, right, as far as density goes, So if a liquid has a density that is less than 1 gram per mil, then it will float on top of water. So ice, for example, has a density of 0.94 grams per mil, right? And so that's why ice floats in water. The reason why that happens is we talked about it last week. When ice freezes, right, it turns into this crystal, and the hydrogen bonds make it further make the ice makes the water molecules further apart, making them less dense. And that's why its density now is no longer 1 gram per mil; it's 0.94 grams per mil, and it floats in water, right? So if you want to get more dense than water, you just need to have a density that's higher than water, which is like maybe 10 grams per mil. So that would be like a metal, That'd be like a piece of lead. You just drop it down. I don't know what lead's density is, but something a lot more dense, and it'll just sink in water. So um, here we go. Your first question for today, which is not a hydrophilic group. Again, the key here is like likes like now, right? We're not doing opposites attract anymore. Like likes like. So there's only one up there that's different from the rest. And while you're doing that, I will log in to see how everybody's answering. I'm feeling a little dizzy today for some reason. Maybe the storm is the hurricane's coming up here, but it's okay. I will power through my dizziness and teach you because it is that important to me. But if I pass out, just leave me there, okay? Just run away. I mean, you should probably get some help. Don't just run away. Oh man, man? I do my stupid code again. Does it even matter when you put in "don't ask for 60 days"? No. Like, does that even matter? No. I'm gonna ask IT about that because that is just why are you even making me? I have to log in too, which is crazy because I just logged in before. Well, good for you. I'm kidding. Did anybody ever watch that show Supernatural? And whenever like something good happens to Sam, Dean's always like, "Well, good for you," which is kind of sad because Sam always has the bad stuff happen to him. Like he gets his soul taken, he dies. Well, Dean dies too. And that's not a spoiler, by the way. They die multiple times in the entire series. They die like 20 times. It's absolutely not a spoiler that I tell you that Dean and Sam die. I used to really like that show too, and then like they they came up with a supernatural being that was like super awesome, and like you were thinking to yourself, and you'll know when you see it. I don't want to spoil it. And well, I mean, but then it's like, how do you beat that? And somehow they beat it. And I'm like, that's just not right. You can't do that. So that's why I don't like it anymore. I know. It's crazy. That's about when I stopped. That's about when I stopped, actually. All right. There's 11 answers in. How many people are here today? Oh, we're missing Kiara. So maybe only 11 today, right? Yeah, 11 today. So that's everybody. Oh, ouch, that hurts. Don't want to mess up my laptop that I just got. Okay. All right. Everybody, most people voted for answer C, which I forgot which one that was. CH, exactly. That's the correct answer, CH. Because CH is a hydrocarbon, right? Excuse me, whereas the rest of these guys right here have, the rest of these guys have an O and an H together, right? These O and the H's together can make it, pretty miscible in water. Water likes it. So, good stuff, good stuff. So some other properties that we have with liquids that we have to discuss too. There's viscosity, right? Which most people know already what that is. But like whenever I have my coffee in the morning, right now I'm drinking tea. Maybe that's why I'm feeling a little dizzy. But normally in the mornings I have coffee, and people ask me how do you like your coffee, and I'm like, I want it as viscous as possible, which means I want it like black and thick, right? Like that's how I like my coffee. Um, so I think the viscosity really takes the, it's really important when you're making like gravy. You don't want to have a gravy that's too liquidy, too watery. It runs all over the place. When you're having a good piece of chicken fried steak, the brown gravy has to be like sitting on there, a little runny, but not like falling off. It needs to be a good covering. Sorry, I've been watching a lot of Hell's Kitchen, and so this is raw. So I'm all about the brown gravy on mine. So whenever we go to Cotton Patch, I get the chicken fried steak, and I'm like, I don't want the cream gravy. I want the brown gravy. He's like, really? I'm like, yes, I want the brown gravy. Okay, so it matches better with for me though. So I like colors that match, but then that would be bad for Hell's Kitchen because they like to have contrasting colors on their stuff. Wow, it looks so colorful. The colors just pop. You know. Anyway, I've been watching a lot of cooking shows too. So this is an example of oil, right? We have SAE 40 oil here, and we have SAE 10 oil here. You can see that the higher the number, right, the more viscous it is, right? And so quite simply, right, the definition of viscosity is a resistance of a liquid to flow, right? The resistance of a liquid to flow. That's what viscosity is, right? Viscosity increases. This is a relationship you need to know because it might be a question on your exam. Viscous viscosity increases with stronger intermolecular forces and decreases with higher temperature. And that makes a lot of sense, right? Because when you have a here's a really good example, right? You say you have some olive oil in your bottle of olive oil, and you're about to pour it into a frying pan so you can make your your steak, right? I like to use butter, but I'm thinking about steak for some reason. But in the bottle, it's pretty viscous, right? It pours super slow, right? But when are you supposed to add the steak to it? Are you supposed to add the steak to it when it's still viscous like that? No, you're supposed to let the heat in the pan, right? Heat up the oil so that it's kind of popping a little bit and flowing real fast. You see the ripples in it, right? And then that's when you know the pan. The ripples are actually tells you that the pan is about 350, 375 degrees, the perfect searing temperature for a steak, by the way. Okay, so that's why you have to do that. If you wait too long, you'll burn the oil. Number one. If you put it in too early, your steak will turn gray. Who wants a gray steak, right? So, and the reason why that is because the heat's too low and it's not the perfect searing temperature for the steak. And so that's why they always tell you pour in your olive oil, right? And wait for you to see the ripples, right? And that's the perfect temperature to slap a steak on there. And so the reason why it's rippling, though, the reason why it's even able to ripple is because the viscosity has decreased enough, right, that the gases are able to make it move like a wave, right? But once you put it in there, it's still kind of like thick going around. Not fun. The, yeah, syrup is very viscous. Yes, syrup is very viscous. Yes. The other thing about it too is that the reason why, also the other reason why too, uh, a lot of people don't realize that water is everywhere, like water vapor is everywhere, and uh, and so even in your frying pan and you have oil, there's water in there too. But then the other thing is that there's water in your steak, right? And when you put it in there onto a frying pan that is too low in temperature, all you're doing is boiling the water on the steak, right? So you're hitting it with like 100 degrees Celsius, right, which is only 212 degrees Fahrenheit, right? And when you boil your steak, all you get is gray steak. It's because you're basically making like a stew, right? You're not searing it. You have to have a high temperature to burn it, right? So that the water evaporates fast, and then you instantly burn the meat, and that's when you get the sear. But if you put it on a low temperature pan, right, at like 100 degrees or 212 degrees Fahrenheit, all you're doing is boiling the water, which is basically making a stew. And if that's how you like your steak, that's great, but it tastes like crap, right? So that's another reason why that it turns gray. It's because you're literally boiling the water in your steak, and you don't want to do that, right? It's a bad time. I don't know if you knew this, but cooking is all about chemistry, right? Right? Like if you go ask Gordon Ramsay, like everything they learn in culinary school is based in chemistry, huh? I like mine medium to medium rare. My best friend Daniel, he used to work at I can't remember the place. It's a huge steakhouse that people know in Texas, and he liked his steaks flame kissed. So literally, he would just go in the flame and take it back out, and it would be brown on the outside, but quite literally inside was still cold.
Yeah, that's how I eat mine.
Oh my God.
That's how I eat mine. It is crazy because I eat everything like that.
Really? I hope you don't eat
Fish
chicken like
like
that.
that.
Really?
No, I have to cook the chicken and the pork all the way through. I don't like it, but I don't want to get no like worm or anything.
Well, I just want you to know though that had anybody ever watched that show House MD back in the day? So before I became a chemist, I was actually a parasitologist, right? And
No, don't tell me. Tell us. Tell us what. Are you telling me that I'm gonna get a parasite?
yeah,
I know that there's a possibility of that.
what kind of fish are you eating that you're eating like that?
Huh?
What kind of fish are you eating that you're eating like that?
Like salmon,
Ooh.
lobster,
I mean, it's not so bad with like tuna and stuff, but with like salmon, so the problem is that there's this parasite called Dibolotherium latum. It's literally the tapeworm of fish. And if you don't cook fish all the way through, right, literally you can get this thing called Dibolotherium latum. So this girl, huh? Well, yeah, but they're not using salmon in sushi. They're using like tuna. I don't do salmon. Well, no, that's different though because they cook it a different way. Like they don't they like use acid or something to kind of yeah. There's
But
that,
then
that,
I also eat just regular salmon where I'm just like, yeah, just sear it.
oh, that's bad.
Like,
Well, if you feel good about that, feel free. But I'm just saying,
hey,
right?
if I get a parasite, at least I'll be skinny.
I always said, I always said that the best like weight loss program is to be on a parasite, to be on like a tapeworm, and then just take some praziquantel, which is the cure for tapeworm, and then it'll kill the tapeworm, and you'll be fine. So,
I know call if I feel like I have a parasite.
but anyway, well, yeah. So in that episode of House, this girl like went to the house, was like, I don't know what's going on. I'm going nuts all the time, and I'm feeling all tired all the time. I feel like I can't get enough, and I don't eat anything, but I don't eat any red meat, so it's not possible that I have a parasite like a worm from a pig or something like that, tapeworm from a pig or stuff like that. And then House is like, so have you done anything like different lately? In the last few days? And she's like, oh well, I did go camping. And he was like, "Did you eat anything while you're camping?" And she was like, "Yeah, we caught some salmon actually, and cooked it on the fire pit while we were camping." And it turned out what he said was Dibolotherium
Wait, so
latum.
you're telling me that salmon is like
Well, I'm not saying that
like
House MD is like the.
so do you think that salmon is more likely to give you a parasite than any other fish?
I don't
Or
know.
than red meat?
I would think red meat would be worse, but I'm not sure honestly.
Okay.
I'm not sure. As far as different other fish, I'm not sure, but I do know for a fact that yeah, that was like 5 years ago before I was a forensic scientist. It's one of those things where you like don't use it, you lose it, right?
But if they come previously frozen, it doesn't matter, right?
Well, you would think
You
that.
have to freeze it at a certain temp.
Yeah, that's what I'm saying. You would think that during the processing process, when manufacturers like capture the fish and they farm it or whatever, it's like farm fish are probably okay, right? Because farm fish are held in pens that are paddocks that are like clean, right? But it's when they're like river fish, right, in the wild, and they're exposed to all kinds of different things. That's when you should worry about it. So maybe the salmon that they use in like for example sushi is like farm caught, for example. I'm not sure. But I do know that fish have Dibolotherium latum. That's the parasite that they have, and it is definitely. Oh, that's what happened. That parasite like migrated from her like intestine, where the tapeworm was supposed to be, went all the way up to her brain, and that's why she was going nuts. Yeah, you should look up that. You should look up that episode. It's crazy. It's absolutely crazy.
You know,
Okay.
I'm gonna be totally honest. That like scared me, but I'm not gonna stop doing it. I'm not. I'm just gonna be completely honest.
See my point. I think my like a lot of people are like you need to get through all your stuff that you need to teach them in Gen Chem too. But I feel like my point in teaching you chemistry is not just to teach you chemistry, but also to teach you how it affects life.
Yeah.
Because then you care about it more,
Yeah.
right? And so I'm not super worried that we don't get through everything. So let's just let's just keep trucking, right? So the other thing that can happen in liquids is this thing called surface tension, and you've seen it before, right? Where you see like a grasshopper or a cricket or something sitting on top of water. Um, and really, what's happening there is that the hydrogen bonds between the water molecules are like so strong that they hold together at the top, right? And they don't burst open because the hydrogen bonds don't want to interfere with the gas molecules above it, right? And so it creates this little skin, right? And so quite literally, you see right here is like the leg of a grasshopper, and here's the hydrogen bonds holding each other together so that the cricket doesn't fall into the water, right? So that's surface tension. So surface tension is mostly um, I was like, why is my vision so blurry? Am I really that busy? But I forgot to put my glasses on. So there we go. I was trying to read what it's up there, like I can't even read it. So surface tension is most commonly seen there, but when you see it in the lab, it's almost like this in the form of capillary action. Okay. Whew, I'm really getting tired. So capillary action is the rise of liquids through narrow tubes, right? And so when you look at, for example, water inside of a test tube, you can see it forms this little U shape right here, right? And when it forms this little U shape, right, that's called the meniscus. And that's where you're supposed to like measure liquids on any kind of measuring, like water measuring device. So if you have like a graduated cylinder, or hell, if you even have like a measuring cup at home, right, you see that the water goes up on the sides a little bit, right? But that's not where you're supposed to measure it at. You're supposed to measure it at the bottom of the meniscus, or that U shape, right? So there's a couple different forces happening here, right? There's the adhesive forces, which attract the liquid to the wall of the tube, and then there's the cohesive forces that attract the liquid to itself, right? If you didn't know, most glass is made of silicon dioxide, right? Most glass is made of silicon dioxide. And so what's happening here with water is that the water molecules, right, are actually super attracted to the sides of uh, the glass, right? And so this is the same reason why when it's raining and you haven't cleaned your windshield in a long time, it seems like the rainwater sticks to your windshield, right? But then you can put the spray on it, and then the rain will just flow right off, right? And the reason why is because water is pretty attracted to glass, right? Like how many times have you poured out a glass of water and there's still water inside the glass, even though you're holding it upside down, and there's still a film of water inside, and it's because water is still very attracted to glass, and so that's why you have it here, right? So water has stronger adhesive forces with glass, right? And that's why it goes up to the sides and you have this meniscus. But when you look at something like mercury, right, which is a metal, this is over here, right? This is the glass right here, right? The gray with the red. So over here we have the gray with the red, which is glass, right? But mercury, being a metal, right, doesn't really get attracted to the glass that much, right? And so here, when you put mercury into a test tube, it actually makes not a U shape, but it makes like a rounded shape like that, right? And so it almost beats up like a ball inside of glass, right? So that's the difference between the different types of forces in this capillary action thing, right? We have the adhesive forces, where the water here is attracted to the glass, right? But you also have the cohesive forces where the water is attracted to itself, right? And right here at the edge, the adhesive forces right here are stronger, and so that's why the water sticks there. But for mercury, the cohesive forces of mercury are way stronger, right, than the adhesive forces with the mercury and the glass, and so that's why the mercury stays kind of like in a little ball on its own, right? Huh? What do you mean it can't be both? It depends on the molecule. These are like two extremes. And then off the top of my head, I can't even tell you something that's like, because you'd have to test it, you'd have to look it up. I don't know. Like, that's not something you do, right? You just get a whole bunch of different chemicals, a gazillion of them, stick them into a tube and see if they have cohesive forces. You know, I mean, maybe that's an experiment someone can do, but I haven't done the experiment, so I don't know what it would be. But these are definitely the two extremes right here, water and mercury. All right. Next question. Next question. Next. Oh my God, I don't have my watch. That's why I feel naked. Maybe that's why I'm dizzy. You ever feel like whenever you don't have all your stuff you carry with you, you feel like unbalanced all the time? You
I
know?
have this really cool bracelet with like anime characters on it,
Yeah.
and I was walking around like doing my daily walk, and I lost it. I
That
don't know how it
sucks.
works.
That sucks.
I went back, traced my steps, and I
rat, whatever. That's terrible. I'm trying not to cuss, remember? Huh? Oh my gosh. You guys, maybe we should have like a cuss jar.
We won't count
Like the cuss jar, right? Like the swear jar. That's funny. That's a good idea. I appreciate that.
or like like
Totally appreciate that.
from the trouble that you've given
I'll think about it. How about?
especially from logging in every single time.
I'm having to do it right now.
Yeah.
It's not just you. Like, but I'm on a computer. You'd think I'd be able to just go in. Unbelievable. All right. 4 responses so far. 5 responses so far. Yeah. Yeah. That's so it's like clearing your cache so that you don't have like a memory of being there before. That's why it's probably keeping you from. That's a good idea, actually. Yes. But yeah, I mean, I always feel like whenever like I don't have all the stuff I usually carry on me, I feel like unbalanced. Maybe that's why I'm dizzy. Back when I was a forensic scientist, I used to carry like a gun on my right hip and a backup on my left. But sometimes I'd forget my backup on my left foot, my left ankle, and I'd be like walking around all like janky because it's all like because I'm unbalanced. So, ouch, it's crazy. That's crazy. I'm so sorry about that. Okay, everybody. Oh, sorry about that monitor. Might have just broken you there. Everybody has submitted an answer, and yes, once again, the vast majority of you have answered correctly. B in hydrogen bonding, right? B is. Oh, I'm going to try to give you the questions. By the way, I'm trying to figure out an easy way to pull them out of the powerpoints and actually give them to you, but I haven't figured that out yet. So it's gonna be multiple choice and handwritten, right? The multiple choice part will be on Blackboard. Oh, you got here a little late, didn't you? That's why you didn't hear me say that. It's gonna be multiple choice. The first part and the second part is handwritten. But once you log into Blackboard, you'll have 75 minutes to take the test, and you can do either part first. It doesn't matter to me. You just need to make sure you have your Blackboard part submitted by the end of the test. Sometimes, but if it makes you feel any better, I'm not gonna try to trick you. So like I know a lot of profs that will give you like calculation questions, and then they'll trick you by having all the right answers, but have like different like units or different like decimal points or different scientific notation. So the first thing you do is you write down, oh, that's the answer because this is what I got, right? But then it's like, what you got the wrong unit. So, but anyway, I'm not here to trick you if that's what you're asking. All right, now we're gonna go to phase changes. Phase changes. Okay. Oh, I forgot to change the thing here. It's. I tell you what, it's weird not carrying a gun anymore. So it's weird. Huh? Back when I was a forensic scientist, did you hear me tell that story just now? I said back when I was a forensic scientist, I used to carry a gun on my right hip and one on my left ankle, and I feel unbalanced when I don't have something that I usually wear every single day. No, I was a forensic scientist. I was in law enforcement. I don't want to get killed out there. That happens a lot, actually. Yeah.
That's how my dad is. He's like, anytime, because he travels a lot for his job, so he's like, anytime I go to the airport, like it's, and like he can't bring his gun, like where he's
Yeah.
going unless he drives. And he's like, it feels so weird.
Well, the thing that you don't know, I mean, you don't think this, but like suspects come back to crime scenes all the time. They love watching you go and clean up their mess and pick up their evidence. That's like a thrill for them. Yeah, absolutely. Back in back in Alabama, I was at a crime scene with a whole bunch of other people in like the woods or something, right? So we couldn't see anything beyond the woods, right? And we were just collecting the evidence. We had state troopers with us surrounding the place. It was all nice and fine, right? But then the state troopers, they had found the suspect, right, or their suspect, And in the interview, the suspect told the state troopers that he was there watching us collect the evidence, and he could have killed any of us at any time. A gun? What else would they use? What? It's incredibly stressful. Yes, it's incredibly stressful. I did it for 5 years, and I'm done with it.
Having like the responsibility to like solve murder and stuff is like really stressful.
When I was in
Like
Alabama,
trying to get answers,
absolutely.
like whoa, like if I don't do this, then and all these people are relying on me. Like
Yeah.
that's a lot of pressure. Yeah.
Oh, that's true, absolutely. But I will tell you that when I was in Alabama, I solved 100 cases. Like that's when I stopped in Alabama. And then I came over here, did a little bit over here, and then I was like, I'm done. So
You said that you like to teach too.
yeah, teaching is fun for me. That's why I teach the forensic science class here.
Yeah, and you're a really good teacher.
Thank you. All right, so if you take my forensic science class, you'll hear all the crazy stories, like the one about the cockroach. Um, so let's talk about phase changes now, right? By the way, if you didn't know this, you absolutely need a degree in chemistry to be a forensic scientist. Don't believe the stories out there where you can just be a CJ person or something and be a forensic scientist. You absolutely have to have a hard science degree to be a forensic scientist. All right, so phase changes, right? So we've talked about this before, right? And we'll just talk about it in a little more detail now, where you can go from liquid solid to gas, right? But the thing I want you to know is that when you're going from a liquid solid to a gas, right? So basically, liquid to solid, which is melting, and then liquid to gas, which is evaporation. You're putting heat into the system, right? So that the molecules get further apart. Okay, does that make sense? So when you're doing that, the molecules get so much further apart that then they evaporate. They don't want to be near each other anymore, right? So if you put enough heat into the system, it will evaporate the molecules because they're so far apart they start repelling each other. It's that same thing I was talking to you about before with the van der Waals chart, right? This thing can be used for everything, right? There's a spot, right, where the molecules like to be with each other, right? But at any other point when there's too much energy, what happens? They just don't want to interact with each other anymore, like over here, right, where they're furthest apart. And so the thing that you need to know, like I said, is that you are putting heat into the solid to make the molecules further apart for it to become liquid. You put more heat into that, and then it evaporates, right? And that's when the molecules are the furthest apart. It happens backwards too, right? Where you can take a gas and cool it down, or you can even use pressure to do it, right? Put it inside of a pressure container, right? And what you're doing is you're going to compress that gas, right, or freeze it or compress it. Either one will work, right? So that the molecules are closer together. And once they get close enough together, what happens? They condense and they become a liquid, right? And then you, you can freeze it even more, and then what happens? It becomes a solid. Give it some more coldness, right? Taking away heat from the system. So in one scenario, you're putting heat into the system to make the molecules further apart so they can go through their phase changes. But then in the other way, the backwards way, you're taking heat away from the system, right? So that the molecules come closer to each other and become a solid. Okay? That's the takeaway message from this slide right here, right? And so you can see here in this really like rudimentary graph right here, which I kind of messed up with my drawing up there, but that's okay, right? Blue is an exothermic process. Oh, sorry, blue is an endothermic process, and we learned this already last couple weeks ago, right? Endothermic processes are ones where energy is added to the substance, right? And then exothermic processes where energy is released from a substance, right? Remember when we put the sodium chloride together and there was that explosion? That was a release of energy, and you got what? Salt, right? Well, the same process can happen here with the phases of matter, and they change, right? So here you have a solid, right? And you're adding energy to it, and it becomes a liquid right here, and you're adding even more energy to it, and it becomes a gas. So you have melting. So another science word for melting, by the way, is fusion, right? And so you'll hear a term I'll say a lot later on in the semester when we talk about thermochemistry and stuff called heat of fusion, right? So just remember that fusion is the same thing as melting, right? Because us chemists are very simple people, right? And we like to name things easily. We also like to have our own language sometimes so people think we're smart. And so we just said, hey, let's just call melting fusion because it sounds cool, right? Uh, for you, um, for you, are there any like computer programmers out here? Anybody a computer programmer? There's this programming language called Cold Fusion. The reason why it's called Cold Fusion is because of this right here, by the way. Okay, no computer geeks, huh? That's all right. So before I was a forensic scientist and before I was a parasitologist, I was actually a computer programmer.
Oh my
So
lord, you are like,
I was one of those that couldn't decide what I want to do with my life.
yeah.
So,
You just decided to like major in everything.
and my parents were not happy about that. Parents are definitely not happy about that because it costs more money for them. Okay, so going backwards, you go from gas, it's called condensation, of course, and then freezing is called a solid. But then we have this thing called dry ice, right? Anybody ever order a steak from Omaha Steaks before, and it comes on dry ice? And then you take the steaks out and you put it in your freezer, and you don't know what to do with the dry ice, so you kind of just leave it there, or explode your pipes by putting it in the sink, right? Um, but if you like just leave it there and you open it up like the next day, all the dry ice is gone and there's like no liquid there at all, right? And the reason why is because dry ice can sublimate. And what sublimation is actually going from the solid phase straight to the gas phase without going through the liquid phase first. And the reason why you can do that is because at certain pressures, right? At certain pressures, frozen. Does anybody know what dry ice actually is?
It's a gas, right?
It is a gas. Dry ice is frozen carbon dioxide. Okay. Dry ice is frozen carbon dioxide. So the gas carbon dioxide, which is what you breathe out every day, right? You exhale carbon dioxide every day, every hour, every minute, every second. If you didn't, you'd be dead. That has a certain pressure in which is our pressure, 1 atmosphere, right? This pressure right here, what we're sitting at, right? Where it doesn't have to go through the liquid stage to get to gas. It can go straight to gas. And the vice versa can happen too. It can go, so a lot of people don't know this. Everybody knows about sublimation, but you can go straight from gas to deposition, which is gas to solid. So back at my old school at Auburn University, we had a dry ice maker, right? Most of the time you have to buy dry ice, but we were so cool we had a dry ice maker. So literally we had this huge, really huge ass like I just cussed again, didn't I? Huge thing cylinder, right, of like CO2, gas CO2, right? And it was hooked up to this chamber, like this airtight, like really strong metallic chamber. And you'd think that if you did anything to this thing, it would explode. But you hook up your little hose, you turn on the CO2, right? And the CO2 gas goes into this chamber that's really strong. Okay, so you're increasing the pressure inside the chamber as the gas flows into the chamber. Okay, and the whole time it's happening, I should record this for you guys sometimes. There's like it's like it looks like it's about to explode. It goes. There's like just it's going everywhere for like 10 minutes. This gas, like white gas, is flowing everywhere. It's freaky, right? And then it finally calms down. There's no more gas. You turn off the cylinder and you open up and there's a huge block of dry ice, right? So it literally goes from a gas cylinder into this chamber, right? And it's dry ice. It's absolutely crazy. So bigger chemistry departments do have dry ice makers, and it's kind of fun. And of course, I just talked about dry ice, and there's a picture of dry ice. I don't know why I do this. I always like jump the gun. So this slide is literally talking about what I just told you. Oh, getting parched. I'm feeling dizzy, but I'm also feeling parched. But I'm so tired. But at the same time, chemistry makes me so excited. So like, it's like a never-ending cycle. Okay, sublimation deposition, right? Molecules in a solid have thermal energy that allows them to vibrate. That's key right there, right? So molecules can do three things. They can either vibrate, translate, or rotate, right? And vibration is exactly what it sounds like. They're just vibrating, right? That's all they're doing, okay? And so surface molecules with sufficient energy can break from the surface and become a gas, and that's called sublimation. So here we have water right here, okay? Oh, it's not water, so we have ice here, and this is ice actually going straight to being a gas, water vapor. Can anyone tell me an example of that happening in your real lives?
Water going turning into gas.
Yes, water going straight to, no, sorry, ice turning straight into gas. Have you ever experienced freezer burn before? Like on your steaks again, or your pieces of meat, or your vegetables that you put in the freezer, right? You ever notice that when you put something into the freezer and then you take it out after a month, it's a lot drier when you cook it? And you're thinking to yourself, why? How did it dry? Everything was ice, right? And it was still,
gas.
yes, the
So
ice.
gas turning into ice.
No, it's ice that turns into gas.
Oh.
Right. Sublimation, right? The ice turning into gas. Because you'll throw a wet, nice, juicy steak into the freezer, right? And most people don't have food saver bags to keep it so that it's like airtight. But most people just put them in a Ziploc bag or a foil thing or something like that, or even plastic wrap. But the problem with that is that when you do that, you put it into the freezer. As you close the freezer, the pressure inside the freezer increases, right? That's why when you're like trying to, sometimes when you close the freezer, it like not decreases, it decreases. When you try to open the freezer, it doesn't open very well, right? Sometimes you have to like pull it really hard. It really happens with the chest freezers. When you put stuff into the chest freezer, you close it, and then you want to open it right back up again, right? There's a vacuum in there, right? So that so the pressure inside of a freezer, along with how cold it gets into the freezer, right, makes it so the ice goes straight to gas, right? It doesn't ever go into liquid phase. It never becomes water inside your freezer. It's too cold in there, right? And that's how you get freezer burn. How do you combat freezer burn? Put it into an airtight container, right? Use a food saver bag, and that way the water can't escape as a gas. It's still in there, right? And you open it up after, if you freeze it for a year, open it up, it still tastes just as good. So, freezer bags, they're good for you. Well, not freezer bags, those are just regular Ziploc bags. Food saver bags, right? Because what you want to do is two things. You want to make sure that the bag that the steak is in is vacuum tight, right? Like airtight, and all the air inside is vacuumed out. That's what you need to do. So yes, not only can frozen CO2 sublimate and do deposition, ice can do it too. Water can do it too. It's crazy, right? It's absolutely crazy. Capturing vapor molecules into a solid is called deposition. Already said that, right? The solid and vapor phases exist in a dynamic equilibrium in a closed container at a pressure below the melting point. Therefore, solids have a vapor pressure. Okay, so the next slide is going to be about vapor pressure. We'll talk about it in a second. I got to take a breath. Okay. Whew. At the very least, you'll learn how to keep your food fresh in this class. Okay, you'll learn how to keep your food fresh. All right, so these are the terms that you're going to be learning about later on in the semester, right? Like even more deeply, but we'll just touch on them here because they're about the changes in the phases of matter. There's heat of fusion, which is the energy required to change a solid at its melting point to a liquid, right? So literally, heat of fusion is the same thing as what? Heat of melting. There's going to be an equation that goes with this, but you don't need to know it for the exam, not this time around. Just know that that's what it means. There's heat of vaporization. That's the energy required to change a liquid to its to a gas at its boiling point. So just quite literally the same thing, right? Okay, quite literally the same thing, except for vaporization now, water vapor. And then lastly, we have heat of sublimation, right? And this is the energy required to change a solid directly to a gas. Okay, a solid directly to a gas. Whew. So all three of these are like and you don't have, this part is not that important. It's not going to be on the next test because we will dive deep into it later on in the semester. But notice that this here, the heat of fusion, right? It's melting, right? And then heat of vaporization is boiling to a gas. But then sublimation is what? It's solid straight to gas, right? They're all numbers, by the way. They're all numbers that you can figure out with an equation, right? But if you look at this here, look at this. The energy of the solid is the same here, right? And the energy of this gas is the same here. The liquid's phase is in between, but the energy between melting and vaporization is the same energy that's what? The energy between sublimation, right? And then the same energy that's between condensation and freezing is the same energy that's required for deposition, right? So what you can literally do is add together the value for heat of vaporization and heat of fusion, and what will you get? Heat of sublimation. That's how you do that, right? Okay, breath. Take a breath. Okay, so back to this slide, right? Literally all we have here then is some examples. We have butane, dimethyl ether, diethyl ether rather, water, and mercury. right? And the thing I want you to notice here, right, is that here's the heat of sublimation, and here's the heat of the green is the heat of sublimation for each of these things, right? But then the red and blue is the heat of vaporization, the heat of fusion. If you add these two numbers together, what do you get? The heat of sublimation, right? You add these two together, what do you get? And it's the same thing for every single compound there. Notice? Oh my God, that's like a Hell's Kitchen thing, because like whenever they call out an order on Hell's Kitchen, Ramsey goes her, and I just said noticed. See? Okay, thanks for that, guys.
Sorry. I feel like you have all these paid partnerships with Hell's Kitchen and
It's even worse when I'm teaching at TCC because I'm always plugging Texas Wesleyan too. I'm like, you could do that at Texas Wesleyan, and you came here. So anyway, but yeah, so that's what I want you to see about that. And then, and these are just the values you get. You'll learn what the equation is to figure out what these values are later in the semester. But right now, I just want you to know that you can add together the heat of vaporization and the heat of melting, fusion, right? And you'll get what? The heat of sublimation. Okay? Next question. This is a molecular diagram that shows liquid water. Which of these diagrams depicts vapor emitted from the pot of boiling water? Boiling water, there it is. 3 responses so far. Ooh, so far it's half and half. I can't wait for you guys to discuss this. So far, only 4 responses. 5 responses. I'm so glad the weekend is coming up for me. Whew. So they're like installing something in my office right now, a TV and some shelves. And let me just tell you, that was the biggest mistake I ever made, asking them to do that. I was kicked out of my office the entire day yesterday because they were in there trying to one person, this guy, who just got his hip replaced. So I don't even know why he's working right now, but he's in there trying to install my shelves. And the first thing after 30 minutes of him working is I hear him cussing. Like really loud. I'm like, what's going on in here out there, right? And so I go in there, and the shelf brackets are upside down. And then so he's like, all F word, F bomb, MF and all this stuff. And I'm like, oh my God, this is why. And then he said, I can't believe I, effing did that. And then I'm like, okay, maybe it's just we'll just let the guy go, let him work a little longer. And so, like another 30 minutes go by, and I hear him cussing some more. And I go in there and I look, and I'm telling you, it's just 2 shelves. It should be like 4 holes max, right? 4 holes max. I go in there, there's 20 holes in my wall, 20 of them. Holy crap. Not only that, he's got a ladder, but he's standing on my desk and there's dust everywhere. And this just kept on going on and on with that all day yesterday. Oh, poor guy. The best part was when he came up here to actually do it. He was like, uh, um, does anybody know where 301C is? I'm trying to put up some shelves in 301C, and we don't have a 301C, by the way. Okay, and so I should have known right then that there was going to be a problem because my office is 310C, not 301C. So it's like I should have known. I totally should have known. And I told my boss about it, and he goes, "You wanted shelves in your office, so thanks for your support, boss. Thank you for your support." Okay, that gave time for everybody. Wow, we have. Oh, she's here. That's why. I was like, last question. There was only 11 people. Okay, so let's see how everybody answered. Wow, it's almost half and half. Well, 2/3 and 1/3, right? So there's a 1/3 here that put C. I'm not going to make you discuss this because I just want to tell you. Um, if you look at this right here, these images, right? The C here is literally hydrogen and oxygen separated from each other, right? So are you really vaporizing anything when you do that? No, you've actually changed the chemical water to hydrogen gas and oxygen gas, right? So it's definitely not C, right? Which is actually really funny too, because this picture right here can't even happen because you have oxygen by itself. There's not even a second oxygen on top on it, right? To make O2. And then you have hydrogen here by itself. So this is actually like a process called electrolysis, where if you put like electricity into some salt water, right, it starts to make bubbles at the ends of the electrodes, and those bubbles are actually separating molecules of hydrogen and oxygen, breaking apart the water. It's called electrolysis, right? That's what that is. Same thing here. This is actually drawn more correctly because now you have two oxygens because O2, because it's a diatomic. Hydrogen is also diatomic too. Remember, it's one of the in the family type of things, right? And so you've done electrolysis here too. So the correct answer is what? It's A, exactly. Because here you still have water molecules, right? And they're further apart than they are up there, right? That's the key to this. When you go through a phase change, you're not changing the chemical, right? You're just changing the phase. It's still the same chemical. Okay? Whew. Okay. This is probably going to be our last slide, maybe the second to last slide. And so we didn't get through everything. So I will the test will end after the last slide for today, and then we'll finish the rest of the slides next week for the next test. Okay. All right. So this is called the heating curve of water. And maybe it would have been nicer if I had shown you this before, right? Because this is literally what we see here, where we have, uh, right here is, does that say negative 25? Yeah, we're at negative 25 degrees Celsius right here. Has anyone noticed that your freezer is actually a lot colder than freezing point? Everybody notice that? Your freezer is actually negative 20 degrees Celsius is what it is, right? But the freezing point of water is 0 degrees Celsius. So let me ask you a question. Why is it that they don't just make freezers 0 degrees Celsius instead of 20 degrees Celsius? Negative 20 degrees Celsius. Huh? That's true. But there's an even more fundamental thing that's going on there, right? At 0 degrees Celsius, right? At 0 degrees Celsius, you're taking heat out of the molecule, right? So that uh, it freezes, right? And that takes a process. It doesn't all freeze at once, right? Does that make sense? Right. So um, when you put, for example, a bottle of water into the freezer, how does the bottle of water freeze? From the outside in, right? Because the heat needs to travel a path, either out of the water or into the water. And the freezer is traveling out of the water, right? But the coldness is on the outside, and so that water doesn't all freeze instantaneously, right? So the problem is that if you're at 0 degrees Celsius, right, there's not enough energy being taken out of that water to keep it frozen all the time. You just have mushy ice cream all the time, right? Honestly, I like ice cream that's a little softer, so I like to put my freezer a little bit like higher, like maybe negative 10, just so my ice cream is a little softer, right? But the reason why freezers are at negative 20 is to ensure that every single molecule of water is frozen, right? Because if you didn't, have you ever been to that store, 99 cents only before? They have like this thing, this open freezer thing of like what they call fresh seafood, but it's like bags of like shrimp, and you see half of it is like melted and half of it is frozen. And you're like, I'm not buying that shrimp. Well, that's because they have their freezer set too high, right? It's frozen. I mean, it's the freezing point of water, but it needs to be far lower for everything to be frozen. Does that make sense? And the reason why I want to say that is because right here is where you're at the freezing point of water, and you have to go all this right here. All this heat right here needs to be taken out before you actually get to a frozen piece of meat or a frozen piece of water, right? Going the other direction, look how much energy you have to put into water, right? Look how much energy you have to put into water to actually get it to boil. That's why they always say a watch pot never boils. It takes forever to put in that much energy, right? A hot pot, a watch pot. Sorry. See, I'm dizzy. I'm like feeling a little lost. No, but isn't the saying a watch pot never boils? Never, has anyone ever heard that before? Am I making that up? Well, I said it wrong the first time, so that's not your fault. But the second time I said it correctly. Anyway, a watch pot never boils because it takes a crap ton of energy, right? This line here shows, right? This line here shows the amount of energy required, right, to be taken out. Sorry, not to be taken out, to be put in to water for it to finally evaporate, right? So while the water is sitting in there right now, while the water is sitting inside your kettle or whatever like there, right? Not all of it is at 100 degrees yet. Some of it's not at 100 degrees, right? The vapor bubbles that you see. Why do you see bubbles when you? Anybody know why? Anybody know why you see bubbles when you boil water? The reason why you see bubbles when you boil water is because the vapor, the water vapor, the gas is bubbling up from the bottom. Why does it bubble up from the bottom and not from the top? Because the hottest part of the pan is at the bottom, right? Are you heating it from the top? No, you're heating it from the bottom. That's where your stove is. That's why bubbles float up, right? Does that make sense? From the bottom? Huh? No, no. Sublimation is so that's evaporation, right? Sublimation is going solid to gas. Yeah. So we're talking about evaporation right now, right? So the key here is to notice this graph here, right? Where it takes energy right here to actually melt, to freeze something. You can pretty much easily go up in temperature, right? You can go up in temperature pretty quickly. It doesn't take as much energy. But once you reach the boiling point of something, it takes forever for it all to boil, right? Same thing here. Once you freeze it, right? Once you get past the freezing point, it's pretty easy. It doesn't take much energy to get down to the freezing point. But when you're in between, right? When you're waiting for it to do it, it takes a lot of energy, okay? And so these pictures up here literally show, here we have water vapor, right? Here we have water vapor at the top and then liquid water at the bottom. So this water vapor is this liquid water is becoming water vapor. Here we have normal water, right? That's number 3 right here. It's getting heated right now. And then here we have ice starting to freeze, right? Or melting, right? Where part of it is frozen, part of it is not, right? And then at the very end, we have here frozen water, which is ice. And you notice how the hydrogen bond makes the uh, the water crystals, right? And it makes these water crystals so that they're so like organized and aligned. And when they do that, there's these little gaps in between, making the water a lot less dense than it is when it's here or when it's here, right? Sorry, when it's water, when it's liquid water, right? And that's why ice floats in water, right? This graph is important. There'll be questions about this graph. So make sure you take a deep dive into that. All right, before we end it, hold on one second here. A couple more things. Just one more slide here. I don't know if you remember I said this before, but molecules of liquid are constantly in motion, right? And they can do 3 things. They can vibrate, they can rotate, or they can translate. Vibration is quite literally just vibrating, right? Rotation is, going around in a circle, right? Spinning around in a circle. And translation is actually moving in space, right? And so this picture shows water, right, at room temperature, but there's always some water that has enough kinetic energy so it evaporates on its own, right? And so I think I said this last week when I was like, whenever I spill something on the floor, I always say, oh, let's just like give free energy deal with it, right? Well, that's what that is. That's the inherent kinetic energy in water that makes it evaporate on its own. So eventually, water will just evaporate. It won't just stay there the whole time, right? It will dry up eventually. Okay. Therefore, the larger surface area, the faster the rate of evaporation. Okay, that's why a puddle on the floor evaporates so fast because it has a huge surface area. All right, this is the last question, and then we'll go talk about lab. What type of molecular motions do most liquids exhibit? Oh, sorry. What type of molecular motions do liquids most exhibit? The most of all of them. And this is literally on the last slide. And then we'll talk about the lab afterwards. I didn't even get to talk about supercritical fluids. That's okay. We'll talk about that next week. It won't be on the test, but we'll talk about it next week. I just want to say I'm very proud of all of you, by the way, because I had to do the attendance recently, the 12th class day attendance, and you're all here every day. So thank you for that. I all had to do was say all here. So, and I know you don't have to be here. You can be at home and just watching the videos. But I appreciate you coming to class every day. It makes me, even when I feel sick and dizzy, have enough motivation to actually come to class to teach you. What is this one called again? Oh, here it is. I've got eight already, 9 people so far. 9 people so far. 10 people. 2 more people, please. Please, por favor. One more person, please. Okay. So, interestingly, right? Interestingly, I'm glad the vast majority of you got it correct, right? Because the question was, what type of molecular motion do most liquids? Sorry, what type of molecular motion do liquids most exhibit, right? And that was quite literally the last slide I had. The answer is A there, right? And the last slide I said right here at the very top of this slide says liquids are constantly in motion. Vibrational is what they do with limited translational and rotational, right? So the answer, well, but the question asked for what does it do the most? That's what the question asked, right? See, what type of molecular motion do liquids most exhibit? Not what do they exhibit, but what do they most exhibit? So in this case, it would be vibrational.